in our last two lectures for current transformer, we have studied some of the basic requirements to understand various terminologies or definitions of errors in the instrument transformers. We have also seen the effect of transients on the performance of current transformer. We also saw what will be the behavior of current transformer if there is a saturation. We saw that there will be peak in the secondary terminal voltage whenever there is the zero crossing of the flux. Okay, similarly, if we want to see that thing during transients, then we have seen that during transients there will be a DC component of the flux. So superposing on this DC component of the flux, this alternating component also, we will see whenever this alternating current component is crossing through zeros, and if let us say the CT is in saturation, then again we will be able to see that there will be spikes in the secondary voltage. Similarly, because of that, the secondary current will be having spikes in that region. Okay, so in this way we can explain the behavior of the CT during transients. We have already seen how to find the actual turns ratio of the current transformer in terms of the nominal turns ratio as well as the magnetizing or the shunt branch current. Okay, we have also seen how to calculate the phase difference between the ideal transformer and the actual transformer. Okay, now let us try to define 2-3 terms of the various errors and related terminologies for a current transformer. The first one is the ratio error. We have already seen a hint of that thing in our lecture number 127. That is, in lecture number 127, I have used two items. One is Kc and other is Kt. This Kt is the nominal turns ratio. Or the turns ratio of the windings, the ideal one. This Kc is the actual ratio. Okay. Now in our lecture number 127, we have seen that we can write Kc equals to Kt 1 plus I naught over Kt Is sin phi s plus zeta over 1 by 2 raised to power 1 by 2. Now this zeta is the hysteretic angle. That is the angle of the I naught, the no load current with the induced EMF. Okay. This was zeta, the angle between the no load component of the current and the flux. Okay. Now, how do we define the ratio error? Ratio error is defined as the ideal ratio minus actual ratio over actual ratio. That is, if I write it as epsilon, then this error, ratio error, this is ratio error, is nothing but Kt minus Kc over kc. This is in per unit. If I want to find it in percent, then I will multiply by 100, then it will be in percent. Okay, so in this way we define the ratio error. Okay, and this is the relation through which we can find the numerical value of the ratio error if we know the nominal or the ideal turns ratio or the nameplate turns ratio, the no load component of the current, the power factor angle with respect to the secondary induced voltage, and the hysteretic angle and the secondary current. Now we also define a next term which is called ratio correction factor. Represented by RCF. Now what does this mean? It means it is a factor which, if multiplied by the ideal turns ratio, or if we multiply the ideal turns ratio by this factor, then we will get the actual turns ratio. Okay, now using this equation, let us say equation number, I will write this as equation number 1, this as equation number 2, and this as equation number 3. Now using equation 2 and 3, we will try to find the relation between ratio correction factor and the ratio error. That we will do in the next slide. Now let us find the relation between RCF and the ratio error. RCF into KT is equal to KC. This was equation number 3, and error was equal to KT minus KC over KC. Okay, so if I take 1 by epsilon or the reciprocal, then I will have KC over KT minus KC. Okay, or 1 over epsilon is equal to KC. I will take KT common, 1 minus KC over KT. Okay, now KC over KT, RCF from equation number 3 can be written as KC over KT. So I will utilize this relation in this equation. So 1 by epsilon will be equal to RCF 1 minus RCF, or solving this I will get RCF is equal to 1 over 1 plus epsilon. Okay, so in this way we have derived the relation between the ratio correction factor and the ratio error. Now we will come to the next term, which is the phase angle error or the phase error. If you refer to the phasor diagram which I have drawn in lecture number 127, then it is pretty clear that the secondary current and the referred current lead the actual primary current by an angle beta. This angle beta is the phase angle error or the phase error. Okay, so it is positive when this secondary current is leading the primary current. Okay, so we can call it as the angle by which the secondary current or the ideal current should be leading the actual current, and it is positive usually for phi s being inductive. Okay, Now we have seen in lecture number 127 that tangent beta had a relation of I naught cos phi s plus zeta over something which was positive quantity, actually ktis plus I naught sine phi s plus zeta. Okay, so in this we can see that this quantity is quite high compared to this quantity, so we can see that denominator is always positive. Okay, so I naught cos zeta plus phi s can be written as I naught cos phi s cos zeta minus I naught cos sine phi s sine zeta. Okay, now this is tangent beta is proportional. I will write it as some quantity k. Denominator is now shown as some positive quantity k. Okay, now you can see that this tangent beta is going to be positive when cos phi s plus zeta is greater than 0, that is it is positive. Okay, now this is positive whenever phi s plus zeta is less than or equal to 90 degree. Okay, and it will be negative when this is more than that thing. Okay, this total sum is more than 90 degree, then it will be negative. Okay, so in that case we will see that a normal lagging load which is usually there on the CD terminals, this thing tangent beta or the beta is going to be positive. Okay, now in the next slide we will study another term called the composite error, that we will see in the next slide. Now let us see what is the meaning of composite error. Usually at very high currents for protective CTs, the IEC standard 61869 part 2 specifies the definition of composite error in place of ratio and the phase error. What does it mean? It means it is the RMS value of the difference between the instantaneous values of ideal current, ideal secondary current, and the actual current, the actual secondary current. If I want to talk in terms of the current referred to primary side, I can write it as this composite error. Let us say I write it as CE. It can be written as RMS value of IP dash T minus IPT, where IP dash and IP are the terminologies which I have used in lecture number 127 for the various currents. Okay, let me again define them here. This was the CT which I showed there. This was secondary current IS, and this was IP dash, and here it was the magnetizing branch or the shunt branch, where this is I naught and this is IP. So these are the various terms or terminologies, and this voltage is EM. Okay. So you can see that composite error is the RMS value of the difference between these. Okay. Now there is another term called accuracy limiting factor. So what does it mean? Practically, it is not possible to design a CT which is going to give you, 100% guaranteed results at all the values of the primary or secondary currents. So there is some limit to the maximum possible guarantee. Okay. So there is a term called accuracy limiting current. It is the value of that current or the maximum value of that current up to which the current CT or the current transformer is going to give the guaranteed error which is told by the manufacturer. Okay. So let us say if I have a CT which is going to have 10% guaranteed error at, let us say, X times of the normal current. Beyond this current, we cannot say whether the error will be 10% or 12% or 5%. Okay. Usually it will be more than 10% only. So this X or XIN is called accuracy limiting current, and this X is called accuracy limiting factor. That is the maximum factor by which the current can exceed the normal value, but the error will remain within the guaranteed limits. Okay. So that factor is called accuracy limiting factor for the given CT. This term is usually used in protective CTs. Okay. Now in the next slide, we will try to solve one or two numerical examples so that we can further grasp the concepts of various kinds of error. Now let us see what is the example. This example was given as an exercise to the students in lecture number 127. So what is that? We are asked to prove that the maximum value of phase error, that is beta, will occur at a leading power factor, or that is the burden is capacitive in nature. Okay. And this maximum value which will occur at a capacitive burden will occur when the KT is equal to KC, that is the ideal transformation ratio is equal to the actual transformation ratio, and the value of the phi s, the power factor angle with respect to the induced voltage, secondary voltage, is equal to minus zeta, where zeta is the hysteretic angle. So now let us prove that thing. We have seen in lecture number 127 that tangent beta can be written as I naught cos phi s plus zeta over kt is plus I naught sin phi s plus zeta. And this is the equation number 1 which I have written in the previous slide. This was also derived in lecture number 127. So Kc is equal to Kt 1 plus twice of Kt is I naught sin phi s plus zeta raised to power 1 by 2. Okay, we will utilize these two equations to derive or prove the required thing in this question. So first what we will do, we will try to find the maximum value of beta. How can we find it? We can find it by differentiating this thing with respect to the power factor angle. We are going to assume that I naught and Is are constant. Okay. So After differentiating, we will put it equal to 0. So what we will have, secant square beta d beta by d phi s equals to kt is plus I naught sine phi s plus zeta squared kt is plus I naught sine phi s plus zeta into d by d phi of I naught cos phi s plus zeta minus I naught cos phi s plus zeta into d by d phi s of the denominator kt is plus I naught sine phi s plus zeta. Okay, so this thing we want to put equal to 0. So 0, this denominator will come here, it will be equal to 0. So 0 is equal to kt is plus I naught sine phi s plus zeta, and this is minus, after differentiation it will become minus I naught sine phi s plus zeta minus I naught cos phi s plus zeta, and d by this thing is constant, so it will equal to 0. 0 plus I naught cos phi s plus zeta. Okay, on solving, what I will have, sine phi s plus zeta equals to minus I naught over kt is. Okay, so it implies phi s will be equal to minus zeta minus sine inverse I naught over kt is. Now this quantity I naught kt is is very small. Okay, because kt is is very large compared to I naught, the primary current, it is approximately equal to the primary current only, and this is only 2% or very small of that. So we can neglect this. So we can write that phi s is approximately equal to minus of zeta. Okay, so we can see one thing, that this phase error beta will be maximum when phi s is approximately equal to minus of zeta. So this thing we have proved. Now we want to prove this thing. Now let us come to this equation. When will this kt will be equal to kc? When this term is equal to this term, this second term in the bracket is equal to 0. Okay, now how to do that? First thing is that I naught should be equal to 0. That is not possible. Okay, so what we can do? We can say that 2 kt is, let me erase this and we will solve it, this equation, for a case when kc is equal to kt in the next slide. Now let us proceed further. Here in this equation I have left the third term, but to prove this thing we will require the third term which we neglected in lecture number 127. The third term was equal to I naught squared kt is square, and it was equal to raised to power 1 by 2. Okay, now kc will be equal to kt when this all term is equal to unity or these two terms are equal to 0. So 2 over kt is. Now I will open the bracket using the binomial theorem. 2 kt is into 1 by 2 I naught sine phi s plus zeta plus 1 by 2 I naught squared kt is squared, and this should be equal to 0. Okay, this 1 by 2 is common. Now this I naught is common here, kt is common here. It implies 2 sine phi s plus zeta should be equal to minus I naught over kt is, or this 2 will come here, it will be equal to like this, or phi s should be equal to minus zeta minus sine inverse I naught twice of kt is. Now similar to the previous slide, we can neglect this term, so we can see that phi s is approximately equal to minus zeta, and for this case we can see that kc is equal to kt. Okay, so we have proved that the phase angle error will be maximum at a capacitive burden, and that burden will be having the angle equal to minus of zeta, and during that period or during that instant kt will also be equal to kc. And it is practically very easy to think also. How to do that? We can see that there are two kinds of error. This is the ideal or the secondary current, and this is the primary current. Let us say I am referring primary current now to the secondary side. Okay, ip is referred to secondary side. Now if it had been ideal, then this ips should have been here only. Okay, so now what we are saying, that this beta is maximum. Now this beta will be maximum when this thing is moving on a circle and IP referred to the secondary side is equal to the ideal one. Okay, so in that case KT will be equal to KC. Okay, but beta will be maximum. That is, the error will only be consisting of the phase angle error. There will not be any ratio error. Okay, so practically it is easier to visualize also. Now in the next slide we will try to solve a very good numerical example which might not be available in any of the textbooks. Let us see that thing in the next slide. Now let us see what is the question. We are asked to find the Phasor form or the vector form of the error in a CT having 500:5 CT ratio, and the winding resistance and the leakage reactance on the secondary side given as 0.01 plus j 0.1 ohm. The burden is equal to, that is, the burden is resistive, 1 angle 0 degree ohms, and the shunt branch impedance is equal to 4 plus j 15 ohm. Now all these quantities are referred to the secondary side. So we need to find the error in the Phasor form. How to do that? It is very easy if we know the equivalent circuit diagram of the current transformer. Now let us draw that thing. Okay, now I have drawn the equivalent circuit diagram of the current transformer referred to the secondary side. The error is just defined as I1 minus I2 over I1. Okay, or it can be simply in the Phasor form written as I0 over I1. Okay, now if we know that I2 is the current flowing, then we can find the voltage EM, okay, and then we can find I naught. So in this way we can find the error in the phasor form. Now EM is nothing but I2 into the resultant of this thing, or it can be written as I1 into the resultant of this and this, both are same, okay. So I can write it as I1 into RS plus XLS plus ZB in parallel combination of Zm, and EM is also equal to I naught into Zm, okay. Now this is equation 2, this is equation 1. Error is simply I naught over I1, so I will divide 2 by 1. It will give me I naught over I1 Zm divided by RS plus JXLS plus ZB parallel to Zm equal to 1, okay. Or I can find I naught over I1 directly just by putting the value of Zm, RS plus XLS plus ZB in parallel to Zm. Now I have already done this thing, so I have found that this comes out to be I naught over I1 on putting the value comes out to be 0.12 angle minus of 65.45 degree, okay. So in this way we can find the phasor form of the error in just using without, in such kind of question we should put the values on the last step only. After cancelling various terms we will find that Zm will be cancelled in one of the terms, okay. So it will come either in numerator or the denominator. So after putting the values we can easily find the value of the error. Now in the next slide let us solve another numerical example. That numerical example is also very good in nature and it might not be available in any of the reference books. Let us see that thing. Now let us see a very good numerical example. It will clear a lot of concepts. We are given that there is a CT which is having maximum ratio error of 10% at 20 times of the normal current. So this 20 is the accuracy limiting factor here, and the normal current given is 5 ampere on the secondary side, okay. Now at this 20 times of normal current, the secondary terminal voltage of the CT is equal to 400 volt. The nominal ratio of the CT is given as 600:5. Now what we are asked? We are asked to find the maximum burden in ohm or VA which can be connected to the CT if the fault current is 5000 ampere. So how to proceed with this kind of example? It will be easier for us if we find out somehow the parameters of the equivalent circuit diagram of the CT. Okay, now we know that this error is nothing but I naught over I1 and it is equal to 10%. Okay. So we know that the value of I naught is equal to 0.1 times of I1 at least at 20 times of the normal current. Now 20 times of normal current is 100 ampere, 20 into 5. So this I naught is equal to 10 ampere. Okay, now we have seen that this I naught has been decided now. Now we can find the value of the impedance of the magnetizing branch referred to the secondary side, because we have been given the value of the secondary voltage, terminal voltage. Okay, so Zm is nothing but the secondary terminal voltage induced over the current in that branch. Okay, so it is equal to 40 ohm. Now we are going to assume one thing, although it is not clear in the question, but to solve further we will assume that this remains constant. Okay, now what we are asked to find the maximum burden value which can be connected if the fault current is 5000 ampere. So if 5000 ampere is flowing in the primary side of the CT, so what will be the current in the secondary side of the CT? It will be equal to 5 over 600, and it comes out to be 41.66 ampere. Okay, now let us say that even at this ampere the error is maximum, because we want to find the limiting value of the burden. So let us take some pessimistic results. Okay, so let us say that even at this current the error is maximum equal to 0.1, okay, or 10%. So it implies I naught will be equal to 0.1 times of 41.66 ampere, or equal to 4.16 ampere. Now we have known that this I naught is equal to 4.16 ampere. Now you see that if this current is flowing in this impedance, then the induced voltage will be equal to 4.16 into 40, which is approximately equal to 167 volt. Okay, now we have found the value of the induced voltage. Okay, now there is one more thing we need to find, the value of burden in ohm. Now the current flowing in the burden will be I1 minus I naught, and all of these are refer to the secondary side. So the I1 current is 41.66, I naught is 4.16. Okay, so the current flowing in the burden will be this current. It implies Z burden will be equal to 167 over this current, and it comes out to be 4.45 ohm. So in this way we can see that the burden can be 4.45 ohm. Any burden less than this value will give very good result, that is error will be very less compared to 10%. Now let us find the rating of this burden on the normal rated current. The VA rating of burden will be simply 5 into the rated current into I square Z. So it comes out to be around 116. So to select the CT, what we will see the CT having approximate rated burden of at least 120 volt ampere. Okay, if this multiplication is correct. Now in this way we can find the maximum possible value of burden that could be connected to get the good results, okay, by just seeing these characteristics. Now in the next lecture we will deal with the classification of various kinds of CTs according to IEEE standard and IEC standard. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.